This is part 5. It's Psych 400 Course Pack, Chapter 15 on SEM1 Path Analysis with Manifest Variables. We are now up to part 5 of my video series on the chapter. We're at page 25, toward the bottom of page 25. The topic is R-squared statistics for competing models. Let's verify. No, that is not page 25. It's page 23. My page numbers are off a little bit. Page 23, toward the bottom, page 23, R-squared statistics for competing models. The real material begins on the next page. On page 24 at the top, we have table 16.3, path analysis results. R-squared statistics for 3 endogenous variables under Model 1, Model 2, and Model 3. Under the heading Model, we have Model 1, Model 2, and Model 3. And we have a major section headed R-squared statistics. R-squared statistics for this endogenous variable, dislike of exercise. R-squared statistic for this endogenous variable, health motivation. And R-squared statistics for this endogenous variable, exercise sessions. What does the text have to say? I am on page 24, halfway down. An R-squared statistic indicates percent of variance in a given endogenous variable that is accounted for by the variables hypothesized to have an effect on it. This statistic is interpreted in the same way that R-squared statistic for multiple regression is interpreted. Its values may range from 0 to 1.0, with higher values indicate that the antecedent variables are doing a better job of predicting the endogenous variables in question. Moving on to page 25. Results presented in table 16.3 are generally supportive of Dr. O'Day's Model 3. The R-squared statistics show that the 2 paths that appear in Model 3 but Model 1 result in a substantial improvement in the model's ability to account for variance in health motivation and exercise sessions. And going back to the table, one of the variables we care about a lot is the exercise sessions variable. With Model 1, R-squared statistic for exercise sessions was not very high. Remember, the ultimate outcome variable that Dr. O'Day wants to predict is exercise sessions, how many exercise sessions a person engages in a typical week. With the various predictive variables included in Model 1, she was only accounting for 15% of the variance in exercise sessions. But when she went to Model 2, where she had added an additional path from antecedent variables to exercise sessions, there was a big increase in R-squared. It improved from 15% to 26%. And when she went to Model 3, in which she added yet another path to the model, R-squared value for exercise sessions increased from 26% to 28%. That is another piece of evidence indicating that Model 3 may be the best of the 3 theoretical models being compared. We're on page 25, section headed Selecting the Final Preferred Model. This chapter has discussed many different criteria that may be used to determine whether a given path model displays an acceptable fit to the data, and to select among several competing models. This section shows how Dr. O'Day might have referred to these analyses and criteria in the results section of her article. Let's skip some of that. On page 26, we have Dr. O'Day's table 16.3, path analysis results, fit indices for the Null model and 3 theoretical models. This is the same table that appeared earlier in the chapter. It's repeated here at this point for convenience. Let's skip down. On page 27, we have figure 16.4. Composite of the 3 models being compared. This is a repeat of a figure that you saw earlier in the chapter. This is the composite of the 3 theoretical models being compared. Skipping down a bit more. On page 28, we have some highlighted text. This is part of the results section of Dr. O'Day's article in which she's describing the results of her analyses. Based on these analyses, Model 3 was selected as the final preferred model. This selection was based on the fact that A, all the causal paths in Model 3 were derived from theory and previous research. B, only Model 3 displayed global fit indices that met all the criteria suggested by Hu and Bentler, and Muller and Hancock. C, chi-square difference tests showed that adding 2 new causal paths to Model 1 and creating Model 3 each resulted in a significant improvement in the model's fit to the data. D, R-squared values for the 3 endogenous variables in Model 3 were of meaningful size. E, values in the residual matrix for Model 3 were near 0. The residual matrix was covered in part of the text that I've skipped over in this video lecture. And F, path coefficients for all causal paths hypothesized by Model 3 were statistically significant. Figure 16.5 presents Model 3. The straight single-headed arrows represent direct effects and are identified with standardized path coefficients. Now this is something new. We go to page 29, and on page 29 we have figure 16.5. This is Dr. O'Day's final model, final preferred model. It is Model 3. It's identical to the figures, the path models that we saw earlier in the chapter, except now she's added statistics to these paths. The path from health motivation to exercise sessions is identified with the statistic 0.17 and 2 asterisks. What is this all about? That is a standardized path coefficient. Its interpretation is essentially the same as a standardized multiple regression coefficient, a beta weight for multiple regression. It's a positive value, meaning that as scores on health motivation increase, number of exercise sessions also tends to increase. 2 asterisks means that it's statistically significant. Specifically, legend at the bottom of this figure caption says 2 asterisks means that it's significant with P being less than 0.01. If we look at this final model, the relative size of these path coefficients indicate which of the antecedent variables have relatively strong effects on exercise sessions, which have relatively weak effects. Notice that lack of time for exercise has a path coefficient of negative 0.36. That's the biggest of any of the path coefficients for any of the paths, for any of the variables that are predicted to have direct effects on exercise sessions. As scores on lack of time for exercise go up, number of exercise sessions people actually engage in goes down. That's what Dr. O'Day would have predicted. As dislike of exercise goes up, exercise sessions go down, but notice it's a smaller path coefficient. Health motivation, we have a positive path. As health motivation goes up, exercise sessions go up. That's what we would expect, not a terribly strong path coefficient. So what we're looking at in this figure are path coefficients on the arrows that represent direct effects. I'm still on page 29. The text continues. Path coefficients in the final preferred model. The direct effect of an antecedent variable on a consequent variable is that part of an effect that's not mediated by another variable. In figure 16.5, direct effects are represented by the straight single-headed arrows. The numbers on these arrows are standardized path coefficients, which represent the size of the direct effects. These path coefficients are similar to the standardized multiple regression coefficients, that is, beta weights, that are obtained in multiple regression. I've added a note in red font here below this paragraph. It says, see page 10 for a definition of standardized path coefficient. I went over that definition earlier in this chapter. If you want to flip back to page 10, you can look at my definition for a standardized path coefficient. Continuing on page 30, positive path coefficients. Statistically significant positive path coefficient is typically interpreted as evidence that the antecedent variable has a positive effect on the consequent variable. Larger the coefficient, stronger the effect. For example, the arrow connecting health motivation to exercise sessions in figure 16.5 is identified with a standardized path coefficient of positive 0.17. Size of the coefficient indicates that for every increase of 1 standard deviation in health motivation, there's an increase of 0.17 standard deviations in exercise sessions. What's he talking about? Look at the figure. Path coefficient is 0.17. It's standardized path coefficient. That means that for every standard deviation that health motivation goes up, we expect exercise sessions to go up by 0.17 standard deviations. And that's while statistically controlling for any other possible effects in this model. That is what is represented by a positive path coefficient. What about negative path coefficients? In contrast, a statistically significant negative path coefficient is typically interpreted as evidence that the antecedent variable has a negative effect on the consequent variable. For example, the arrow connecting lack of time for exercise to exercise sessions is identified with a standardized path coefficient of negative 0.36. Size of the coefficient indicates that for every increase of a standard deviation of lack of time for exercise, there's a decrease of 0.36 standard deviations in exercise sessions. Interpretation is essentially the same, but it's in the opposite direction. Standardized path coefficient negative 0.36. That means for every standard deviation that lack of time for exercise goes up, number of exercise sessions goes down by 0.36 standard deviations. That is what a negative path coefficient means. And we can skip some. This is a good place for us to end part 5 of our video. There's more material to cover. I'm on page 31. Direct effects, indirect effects, indirect effects, and total effects. Let's cover that in the next part of our video series. This is the end of part 5 of my video series. There will be a part 6.